great session yesterday, and we're going to have an equally great session today. Quite a diversity of presentations. And the first one that we're going to get up here is Robert Holmes. Now, some of you might remember Robert Holmes because he was the swamp coordinator at Region 5, Central Valley Regional Water Quality Control Board, so you might remember from that. And then he came over to the good side, to Fish and Game 7 years ago, so he was able to advance, and he's, I'm sure, happy to be there at Fish and Game. So, and Robert, you're involved with the exotic fish, or you do a lot of electroshock. Instream flow, that's right. Oh, it's Jay that does the other thing, that's right, the electroshocker. Okay, so we're going to get started with Robert Holmes' presentation on assessing aquatic habitat connectivity. Robert?
Okay, thanks, Jim. Today I'm going to be talking a little bit more about in-stream flow type methodologies. It was sort of the topic of in-stream flow was brought up here and there throughout the talks yesterday, or at least referenced in some of the talks as far as indicators. And I'm going to go over just a couple of the types of methods that we have to address certain components of in-stream flow. And the outcome for today that I'm hoping is that you all will have come out of here with more of a general understanding of some of the types of methods that are available to assess aquatic habitat connectivity and also low flow ecological thresholds. And then when you're selecting and using those types of methods, what are some of the considerations that you should have? And then lastly, I want to also let you know where to find more information, a number of the tools that I'll be going over as far as standard operating procedures. We have guidance documents and fact sheets and checklists. A lot of the stuff that I'm going to be talking about today, we actually have protocols that you can find and use. And some of them are relatively quick and easy to use, and some are a lot more complicated. And ultimately, really one of the main things that I want to get across is really there's no really one best flow for everything. And the whole idea is to think flow regimes and multiple flows to satisfy multiple components of the ecosystem. As far as in-stream flow, what is in-stream flow? Why is it important? Basically, in-stream flow is the water flowing within a stream. Most streams have some level of flow, but there's really no guarantee that all is well for the organisms and the humans that depend on it. And so that leaves natural resource managers faced with a very complicated task of protecting and restoring public values to the rivers while honoring existing uses of those waterways. A good understanding of how in-stream flow levels and regimes relate to the beneficial uses in the services of the rivers, water supply, biological productivity, recreation, and so on is really a necessary step for informed river management. A little terminology. So I mentioned in-stream flow, and that's basically the amount of water in a stream to provide for in-stream uses within the channel. There's also a term that's going around, there's a lot of terms. Ecological flows is another one. Those are flows in water levels to sustain the ecological function, basically the flora and fauna in the habitat that supports those flora and fauna within the stream. Environmental flows are different. Sometimes they get used interchangeably, but environmental flows are the flows that sustain the freshwater ecosystem as well as the human livelihoods that depend on those ecosystems. Anytime you're looking at addressing anything to do with in-stream flow, there's 5 basic components that we look at. Biology, connectivity, geomorphology, hydrology, and water quality. Probably one of the most overlooked components is connectivity, and that's going to be something I'm going to be talking about today. And touching lightly on biology, by far most of what we do at the Department of Wildlife is components and tools to look at biological flow needs, but we also have to look at some of the other factors because those are important for supporting the habitat that's needed. Step one, and so I'm going to go through just some general steps. If you were going to apply some sort of a field approach and go out to these rivers and collect data to actually look at in-stream flow needs for connectivity and ecological low flows, these are some of the preliminary steps you would need to do. I'm going to be talking about some more methods also where you actually don't even have to leave your office and you can get an idea of general idea of some flow needs. So step one is basically to create an inventory of the habitat that's within the stream. This is common to most methodologies. Basically what you do is start at the very bottom of the stream, work your way up, and measure the different types of habitat, such as the runs and the riffles, glides, pools, that sort of thing. And this is really important today because I'm going to be talking about connectivity and low flow thresholds, and those are both determined at riffle sites. And so to have a good idea of how many riffles you have and how long they are and how much area they comprise of the stream, you kind of need to know that when you're selecting sites for doing that sort of assessment. And then step two, you've got to have a good understanding of what unimpaired flow conditions are, and that can be quite challenging. So in some cases you don't have good gauge data or it doesn't go back very far, but that's a really important thing that helps. It can help you in determining when to sample, how often to sample, and then if you end up using any types of models to evaluate your data, they generally need to be calibrated with various flows that are representative of the river. And then step three, this is kind of the final thing of importance. You really need to know like what you're looking at, or what are the species that you're interested in. If it's just general ecology, or is it individual species and individual life stages. So if you're interested, for example, here in adult steelhead spawning, then you'd be looking at roughly a time period. This is a Central Crest River from December through May. So that would be the time period that you want to look at. How often do you have the timing, the magnitude, the duration of the flows that would support spawning during that time period. Juvenile rearing, on the other hand, for salmonids, steelhead in particular, in this river is year-round. So when we're looking at identifying flow to support that, then we want to be looking at complete year-round, and generally the summer is the tricky time. So why is aquatic habitat connectivity important? Basically, habitat can become fragmented either naturally or anthropogenically in nature. It can block nutrients, transfer of energy, and all in all it results in a total reduction in the amount of habitat for organisms to carry out their life cycles. And at low flows, critical riffles, which are natural riffles, basically they can disrupt life history for salmonids. Particularly, they can prevent adults from moving to spawning areas, prevent juvenile salmonids to move between adequate rearing areas, escape predation, and also prevent smolts from moving downstream to staging areas. Anytime you're assessing aquatic habitat connectivity, it's important to specify which of the four dimensions you're most interested in. There's lateral, side-to-side, vertical, sort of groundwater, surface water interaction, longitudinal, which is through the riffle, which is what we'll be looking at today, and then through time. And also you want to identify which elements you're interested in. Today we're going to be talking about organisms, but equally important is the chemistry, the bed load, and the overall energy in the stream. And then specify the time and duration needed, and generally other tools are generally needed to look at other types of components of the ecosystem needs there. So aquatic habitat connectivity, most methods involve site-specific data collection for obvious reasons. All the sites are different. Some riffles could be 200 feet long, some could be only 50. There could be a lot of different things going on. Did want to let you know that the State Water Board North Coast Stream Policy does have a desktop formula that you can actually use and plug in the depth criteria for the fish that you're interested in, and then I believe it's some watershed data from the river, and also I think it's latitude, and it can give you a real quick estimate of, okay, are we meeting passage flows for for adult salmonids, for example. So you can do that really quick and easily from your office. Today I'm going to be going over two other methods. One, an empirical, a site-specific, which is a critical riffle analysis. And then another one, which is hydraulic habitat modeling, which is more complicated. And you can generally look at larger, with the two-dimensional modeling, you can look at larger segments of river. The critical riffle analysis basically is a way to look at sites that are particularly sensitive to flows and that may block or disrupt movement of aquatic organisms. And basically all you need is a stadia rod, tape measure, and you run the tape measure across from the shallowest course from bank to bank, and you take depth measurements at a variety of different flows, and then you compare that to depth criteria, and then you're able to get a relationship between flow and habitat, passable habitat, and you use that to derive a flow. It's based on a methodology from Oregon Department of Fish and Wildlife, and you can use depth and velocity. Usually it's minimum depth that's more the focus, but you also, if you collect velocity data, you can ensure that you're not going to have any high velocity restrictions as well. Generally it takes 4 to 6 sample events. The transect follows the shallowest course of bank to bank. And the other thing is too, the State Water Board does have depth criteria, and we use those depth criteria as well. And they're thought to be a protective flow because they have an additional 1/10 of a foot added onto the body depth of the fish to prevent abrasion. And there's 2 metrics that are used. Basically the percent total of across the transect and the percent contiguous to arrive at the passage flows. And one of the take-homes from this is really, like, a lot of people like to think, oh, this is a minimum flow. It's really not a minimum, it's a protective flow. And it's really just to promote physical movement of those fish across the riffle sites. There's a lot of other factors that are important, including length of the riffle, rest areas, condition of fish, temperature of water, that sort of thing, that you want to look at in an overall migratory success evaluation. And these are just some examples of some of the critical riffle sites. You can see as flows start to go down. These are on some of the central coast rivers. Start to see some of these kind of bands of cobble, and they range anywhere from usually 10 to 25 feet wide or wider. Here's an example. It was up on the Mad River about a month ago. This is an example. So this is lower than what this methodology would give you, and it's more of a belly scraping flow where this fish is about half out of the water moving through. I will also mention that the procedure that I'm referencing here also gets used quite a bit for determining low flow fishing closures. And so at this flow right here, I believe it's 130 CFS, and the low flow closure is about 200. And so it gives you an idea to be protective and to prevent anglers from being able to snag those fish as they come through these real depth sensitive sites. It makes a lot of sense. 2D hydraulic habitat models is one other tool that we have to evaluate passage. It's more complex and more equipment, but it's getting more and more user friendly and easier to conduct. Some of the equipment, a total station, a prism, you basically want to survey the bed topography, tie in vertical benchmarks, survey in some basic elements such as the stages 0 flow and then the water surface elevation. And then you use that information, the bed topography, to construct a mesh of the site, and then the mesh gets used to create habitat models. And the models are really useful because they allow you to look at things incrementally and to look at flow under a bunch of different scenarios. You can look at depth, you can look at velocity, you can look at a lot of things, whereas some of the other procedures only allow you to give you one number. This you can do incrementally, and if you want to look at habitat suitability, for example, you can scale that based on water availability, whether it's a dry year or wet year, that sort of thing. This is an example of an overview of a critical riffle complex in which there's 4 riffles going through this site. The 2D model on the right side helped us evaluate, okay, which one of these channels dries up first, which is the last channel that's the most likely to support passage. Some of the general model considerations is you've got to have an accurate representation of bed topography. And so that's really critically important. If you don't, then the model's only as good as the data that are used to construct it. And then really ultimately, you're going to need other tools to look at other elements of the flow regime. So now I'm going to move on to the low flow thresholds. Why are low flow thresholds important? Basically, low flow is it's a cutoff value. It's a sort of the floor value of what's needed to maintain the ecological value of that stream. The Department of the Canadian EPA has just adopted a methodology that I'm going to go over here in a minute called the presumptive standard. And basically I'm going to go over two hydrological methods which you can use in the office, and then there's what's called a single transect or a field method, which you can go out relatively easy and apply in the field to get an idea of these low flow. What is a low flow threshold? One of the most traditional methods is called the Tennant method, and the Tennant method is based upon a certain percentage of the flow. I believe there's a mean annual and a mean monthly flow that can be applied to get an idea of what that value should be. A lot of people think that that's really a one flow thing, but really Tennant intended for that method to set a range of flows. So you might set a range during a certain time period, over a certain season, or a certain month. And generally, if you can see, to maintain the same level of habitat during the winter time is what it takes to maintain in the summer. It actually takes more water in the summer to maintain the same level of habitat condition in the summer than it does in the winter, because there's generally more water in the winter. So the Tennant method is one method. It's used to set a threshold flow. It's really easy. If you have stream hydrology data, you can use that to assess what the low flow threshold is. And one of the good things about it is it's been challenged many times, and it's generally an accepted method. So that is a tool that you can use. A key consideration anytime you're using any type of hydrology data that's based on hydrology is that you have a good representation of what natural unimpaired hydrology is, because if you're basing it on the hydrology that you have today, maybe with diversions and that sort of thing, you may get an underestimate of what's actually needed. The presumptive standard is the approach coming from Brian Richter, the Nature Conservancy, and it was adopted by the Canadian EPA. And basically it says there should be no more than 10 to 20% flow alteration at any one time, and then to evaluate the low flow threshold is basically 30% of the mean annual discharge. If you want to extract water below that 30%, then it requires a detailed study. So this kind of gives an idea of what that would look like with a natural hydrograph, no more than 10%, and then you can see the 30% of the mean annual is right down here. And then this zone right here, which every stream you're going to see this probably in the summer, is the zone of highest risk. And so if you're going to be dropping down under that, and naturally these streams do, you probably want to do some more detailed studies. So now I'm going to go over, that's just generally based on hydrology. To follow up, using the field method, we have what's called single transect methods. The wetted perimeters one, it's very low to moderate effort. It's been used a long time. It's basically only useful to set threshold flows. What you can't do is like with a model where you can look at different flows and identify trade-offs. You can't really do that with this sort of thing. And with most all these other methods, you do need other tools to look at other riverine elements. For example, the low flow threshold, a lot of people like to think that that's actually a flow that's needed to support, say, salmonid rearing during the summertime. And it's actually not. Like, that requires different methods. It could give you the same answer. It could be higher, it could be lower, but it's a different question. The wetted perimeter method, basically it gives you a low flow threshold, basically to look at the ecology of the stream and what's needed to support just the stream function, the benthic invertebrates as the sort of the core value for the stream. And basically there's a couple of ways you can do it. Most involve field methods. You can either sample it 3 times and input your values into, or as little as 1 time actually, and use a fairly simple hydrology model, and you can calculate what that value would be, or you can go out and not use any type of model and just basically sample 5 or 6 times and develop that relationship yourself. And so what happens is, then what you do is after you've gone out and you've sampled, so this would be, for example, at 4 different flows, you're developing a relationship between the wetted perimeter of the stream and the flow. And basically, this is sort of an ideal curve right here. Not all of them look like that, but some of them do. And what we do is, to get the low flow threshold, basically we're looking at that first point of maximum curvature called the break point. And a lot of streams have this too. It's an upper inflection point. Some refer to these incipient asymptote. And so these are 2 really critically important components of maintaining productive riffle habitat for benthic invertebrates. And right between these values, this is really the critical flow range that you want to be. And then the flow threshold value would be this one right here, the first breakpoint. Overall considerations, so just to sort of start wrapping up, basically every situation is different, a lot of different questions. Some of the key stuff that you really have to consider when you're identifying these flow levels is that you always have to have consideration for what natural water availability is. You know, for example, now in a drought year, different water year types, it's going to be different. That's the advantage to some of the techniques. It allows you to do that. Other techniques you can't. Habitat connectivity and low flow thresholds, as I mentioned earlier, they're not always there. They're not there. You know, they're not there this year under these low flow conditions. Basically, a good approach is just to use a combination of methods to address specific endpoints and look at things at specific times of the year. So just to kind of recap, how does one determine how much water a river needs? Basically, there's not just any one flow, but you want to use a combination of things: hydrology, biology, connectivity, geomorphology, and water quality. Inter and intra-annual flow prescriptions are needed to preserve the ecological health of the river, and we want to always think flow regimes, not any one flow. Just some acknowledgements are flow group at CDFW, CDFW Biogeographic Database, Fish and Wildlife Instream Flow Group, Moss Landing QA Research Group, and the Instream Flow Council. Did want to mention that if any of you are interested, we are planning our 3rd national meeting for the Instream Flow Council. It's going to take next year in April of 2015 in Portland, Oregon. And one of the key things for the workshop is to discuss how to focus on dealing with uncertainty in data collection and methods and that sort of thing. One of the things we often get caught up in is when do you have enough data? How do you know when to stop? You know, how do you balance what you need and, you know, doing the complete Cadillac to the other end of the spectrum. So with that, that's my contact information. Most all these I have protocols on our website, which is available, and you can feel free to call me at any time. We do trainings, field trainings as well. So, thank you.
We really don't have time for questions, but Robert's going to be here all day. You might ask how this might get integrated as an indicator from the session from yesterday. I think that'd be good. We had to, cut off questions for Robert Holmes. So does anyone remember his presentation? And we have a few minutes, because I have one. Robert, are you back there? Yeah, anyone have a question? Because I have one if you don't. Robert, I want to know how extensive is the Instream flow program? You know, how many different stream systems have these requirements set up for them? And do you have any idea how it can be integrated into, well, integrating into the index? Like, you know, from the presentations we had yesterday, is there any way that you see from the presentations yesterday how that information for fish and wildlife could be integrated as an indicator?
Yeah, I mean that's a good question. We're obviously one of the things that we're working towards is standardization and data comparability, consistency, just so that you know when you use a particular method that the data quality is there, that you may help you to answer the question that you're interested in. But we do have studies throughout the state. There's a priority stream list which is on our website, and there's about 21 streams that are spread throughout the state, and there actually is way more priority streams than what's on the list. We had to kind of balance between all the regions. I think Region 1 gave us 20 of their own, but we had to sort of select from that. And then it's really all driven by resources and when we can get money to do studies. Currently I'm actually the only guy to represent coastal streams, anything outside of the Sacramento-San Joaquin Delta. So a lot of what we try to do then, we do have a Delta group which works in Delta tributaries. They have studies in Mill Creek, Deer Creek, and Butte Creek. And so that information's coming out. All the studies, they're different. They have different things going on. In the Central Valley, a lot of it is passage, temperature issues, that sort of thing. But ultimately, we will have members, and there's a lot of good information that could be used to assess these water bodies and the information that we're collecting. But the stuff that I presented today, there's the hydrological, there's a lot of other endpoints other than what we're collecting that other people can collect as well. And maybe those can be put together in some sort of an index of, overall in-stream flow, requirements, or I don't know if we want to say requirements, but something along those lines.
Well, if there's no other questions, we'll break and be back here at 10:45. In your seats.